Hundreds of small earthquakes have been detected at Mount Rainier, and this is the largest swarm of quakes.
Battling Mount Rainier over the last 2 days, this is the largest swarm since 2009.
Molten rock surging upward beneath the snow-capped slopes of Mount Rainier has forced the United States Geological Survey to issue its highest level of volcanic alert. In a move that instantly captured the attention of geologists, emergency planners, and communities across the Pacific Northwest, the agency confirmed that a sudden and measurable uplift in the mountain's surface has been detected by satellite monitoring systems. This deformation, an actual bulging of the volcano's edifice, is one of the clearest signs that magma is intruding into the crust at shallow depths. Before we start, smash the like and subscribe buttons for more updates. For a peak as massive and glaciated as Mount Rainier, such an event carries enormous implications. The uplift is not a subtle tremor of rock hidden in the data. It is a pronounced and accelerating change in the mountain's shape that satellites equipped with radar interferometry have captured with precision down to the millimeter. These measurements reveal that an area on Rainier's western flank has risen significantly over the past several days, an unmistakable symptom of underground forces at work. Volcanologists have long warned that the Cascades, and Rainier in particular, are under constant geological stress. But to witness such rapid deformation in real time signals a fundamental shift in the volcano's internal state. The choice to raise the alert level to red is not taken lightly. In the USGS system, this classification signals that a volcano is exhibiting signs of imminent or ongoing hazardous activity. While no eruption plume currently darkens the sky above Rainier, the agency's decision reflects the seriousness of the geophysical indicators. Ground-based seismometers have registered a swarm of low to mid-magnitude quakes clustered beneath the summit and extending into the edifice's plumbing system. These earthquakes, combined with the sudden uplift, point toward magma movement rather than mere tectonic adjustment. Mount Rainier's location makes this development particularly concerning. Towering over 14,000 feet above sea level, it is the most heavily glaciated peak in the contiguous United States. Beneath its serene crown of ice lies a history of explosive eruptions and massive lahars, volcanic mudflows that can thunder down valleys at terrifying speeds. Unlike lava flows, which generally move slowly enough to allow for evacuation, lahars can obliterate communities in minutes, fed by the rapid melting of snow and ice. The mountain's proximity to densely populated areas, including the cities of Tacoma and Seattle, turns any significant change in its status into a matter of national attention. The sudden deformation detected by satellite is a direct window into the pressurization of Rainier's magma chambers. These chambers are not hollow voids of molten rock, but complex networks of partially melted material and volatile rich fluids. When new magma intrudes from deeper in the crust or mantle, it can force the surrounding rock to swell. If the influx is rapid, the mountain's outer flanks can lift visibly, creating the very bulge now confirmed by orbital measurements. This bulging is not merely cosmetic, it stresses the rock, fractures existing pathways, and can create new conduits through which magma may ascend. Scientists have long used GPS stations on Rainier's slopes to monitor subtle changes in position, but the advantage of satellite radar interferometry is its ability to see the entire surface at once, even in poor weather conditions. The technology works by comparing successive radar images of the mountain taken from orbit, revealing changes in surface height with astonishing accuracy. In the case of Rainier, the most recent comparisons show that the uplift began abruptly, suggesting a sudden surge in magmatic activity rather than a slow, steady pressurization. This rapid onset is one reason the USGS moved so quickly to raise the alert level. Such activity in a volcano of Rainier's size is not without precedent, but the mountain's last major eruption occurred centuries ago, and its quiet snow-clad slopes have lulled many into underestimating its potential. Historical accounts and geological evidence reveal that Rainier is capable of producing eruptions on par with, or even exceeding, the explosive power of Mount St. Helens in 1980. However, the greater threat here may be the collapse of parts of the volcano's structure under the force of internal pressure, sending torrents of mud and debris down river valleys already identified as high-risk lahar zones. The dynamics of the uplift itself provide clues about the nature of the magma beneath the surface. Magma composition plays a major role in eruption style. The more silica-rich the magma, the more viscous it becomes, and the more gas it can trap. Rainier's magma tends toward the andesitic to dacitic range, making it thick and prone to building pressure until it is released in explosive bursts. The speed of the uplift, therefore, may indicate that gas-rich magma is pushing upward, unable to escape gently. In such a scenario, even minor breaches in the volcanic system could lead to ash columns, pyroclastic flows, or structural collapses. From a geological perspective, Rainier's deep roots extend into the subduction zone, where the Juan de Fuca plate dives beneath the North American plate. It is this tectonic collision that fuels the magma supply of the Cascade Range. When slabs of oceanic crust are forced downward, they release water and other volatiles into the overlying mantle, lowering its melting point and generating magma. That magma then rises, occasionally pooling in crustal reservoirs before finding its way to the surface. The current uplift could signal that one of these reservoirs has been replenished to a critical threshold. The USGS decision to issue a red alert also reflects the integration of multiple data streams beyond just deformation. Gas emissions from Rainier's fumaroles, vents where volcanic gases escape, are under constant surveillance. In recent days, sensors have reported elevated levels of sulfur dioxide, a key volcanic gas that often rises when fresh magma nears the surface. Thermal imaging has also detected localized heating in areas adjacent to the summit crater, indicating that hot fluids are moving through the system more vigorously than before. Together, these signs paint a portrait of a volcano whose internal equilibrium has been disturbed. One of the more remarkable aspects of modern volcano monitoring is the speed at which these changes can be detected and confirmed. The combination of satellites, ground sensors, drones, and even infrasound arrays allows scientists to construct a near real-time picture of what is happening inside a mountain that, to the casual observer, may appear tranquil. In Rainier's case, the snow still gleams white, the forests at its base are calm, and no plume mars the summer sky. But the data tell a very different story. The sudden uplift's implications extend beyond the immediate hazard potential. For geoscientists, it offers a rare chance to observe the early stages of a possible volcanic episode in a heavily monitored environment. This provides invaluable insights into the sequence of events that precede eruptions in large stratovolcanoes. Each measurement, from the smallest tremor to the most minute change in slope, becomes a piece of the puzzle that can refine models of volcanic behavior. This, in turn, informs how future alerts are issued and how emergency responses are crafted. For local communities, however, the uplift is less a scientific curiosity and more a reminder of living in the shadow of one of the world's most dangerous volcanoes. The mountain's river valleys are lined with towns, infrastructure, and major transportation routes. The very beauty that draws hikers, climbers, and tourists to Rainier each year masks the volatile processes beneath. A sudden shift from dormancy to activity could disrupt not only the immediate vicinity, but also air travel, commerce, and water systems across the region. Emergency planners are already factoring the uplift into their readiness calculations. While the alert does not guarantee that an eruption will follow, it does mean that the probability has increased sharply. Routes for evacuation, communication strategies, and coordination between local, state, and federal agencies are now under active review. Schools, hospitals, and critical facilities in Lahar-prone zones are reassessing their protocols. The uplift is, in effect, a giant natural warning flag unfurling above the Pacific Northwest. The geological record of Rainier underscores why such vigilance is warranted. Past eruptions have triggered massive lahars that reached as far as the present-day location of Puget Sound. These flows carved new channels, buried forests, and reshaped entire valleys. The Osceola mudflow, one of the most notable events about 5,600 years ago, transformed the landscape over an area of hundreds of square miles. It originated from a sector collapse on Rainier's flank, a scenario that could be precipitated by the kind of structural stress now building within the mountain. Satellite images taken over the past week show subtle but measurable distortions in the mountain's symmetry. While invisible to the naked eye on the ground, these changes are unmistakable when viewed in time-lapse sequences from orbit. In some frames, the western flank appears to lift relative to stable reference points on the surrounding terrain. This deformation pattern matches simulations of magma intrusion at depths of less than 5 kilometers. shallow enough that surface breaking activity becomes a real possibility if the pressure continues to mount. The timing of this uplift adds another layer of urgency. Late summer conditions mean that glacial melt is already elevated, filling rivers and streams that would be prime conduits for lahar flows should they be triggered. Warmer temperatures can also destabilize ice cliffs and seracs on the mountain, making them more prone to collapse under seismic or volcanic shaking. Any eruption or even a large slope failure could instantly melt vast quantities of ice, producing torrents of water and debris with little warning. From a technical standpoint, scientists are now modeling the volume of magma that could account for the observed uplift. Using deformation data, gas measurements, and seismic wave analysis, they estimate that a substantial pulse of material has moved into the shallow crust. The exact volume remains uncertain, but early figures suggest it is not trivial. If this magma remains trapped, it may cool slowly without reaching the surface. If it finds a pathway upward, the release could be explosive. Public perception of such alerts is a delicate matter. Too cautious a warning and people may ignore future alerts as false alarms. Too slow a response and the consequences could be catastrophic. The USGS's red alert in this case demonstrates a willingness to act decisively when key indicators align. It is a calculated decision based on the convergence of deformation, seismicity, gas output, and thermal changes. Each of these alone might warrant heightened awareness, but together they form a coherent and concerning narrative. What makes this event so captivating, even for those far from the Pacific Northwest, is the reminder that the Earth's surface is not static. The forces now reshaping Rainier have been at work for millions of years, building mountains, carving valleys, and fueling cycles of destruction and renewal. The current uplift is just one chapter in that ongoing story, but it is a chapter playing out in a time when we can watch, measure, and anticipate in ways that earlier generations could not. In the coming days, satellites will continue to sweep over the mountain. Seismometers will hum with the record of each quake, and gas sensors will sniff the air for changes in composition. Every data point will feed into the evolving assessment of what the uplift means and how it might develop. For now, the mountain stands quiet in appearance, its white slopes reflecting the summer sun. But beneath that calm exterior, molten rock is on the move, and the land itself is rising to meet it. The red alert is both a signal and a challenge. To watch closely, to prepare thoroughly, and to respect the restless giant that towers over the northwest. The sudden uplift of Mount Rainier has introduced a new and pressing chapter in the geological watch over the Cascades. Now that the surface of the volcano is measurably shifting, scientists are turning their attention to the deeper mechanics at play. Mechanics that are hidden beneath miles of rock, but which leave their fingerprints on every sensor and instrument aimed at the mountain. The most intriguing aspect of the deformation is the possibility that the magma intrusion is not a singular pocket, but part of a broader pulse of molten material threading upward through a complex network of fractures and conduits. Beneath Rainier, the crust is far from uniform. Decades of geological mapping, seismic imaging, and drilling in nearby regions have shown that the rock layers are a patchwork of ancient volcanic deposits, hardened intrusions from past events, and zones of hydrothermally altered rock that are weak and crumbly. Magma does not move upward in a straight line. It exploits weaknesses in this patchwork, pushing aside softer material and sometimes stalling in pockets known as sills or dikes. The newly observed uplift could be the surface response to one such dike injecting itself horizontally into the upper layers of the volcano, a process that has been documented in other stratovolcanoes before major eruptive sequences. The chemistry of the gases escaping from Rainier's vents offers another key to understanding the change. Instruments have recorded not only elevated sulfur dioxide, but also shifts in the ratios of carbon dioxide to sulfur and water vapor. This chemical fingerprinting is more than an academic exercise. It reveals the depth at which the magma is releasing its volatiles and whether that magma is fresh from deep sources or recycled from earlier eruptions. In this case, the gases bear the hallmarks of a deep, relatively undegassed magma body, which means that it has retained a high concentration of volatile components. When such magma rises and the surrounding pressure drops, those gases expand violently, driving explosive eruptions. Volcanologists are also scrutinizing the thermal evolution of Rainier's glaciers and summit snowpack. Even a small increase in geothermal heat can destabilize vast amounts of ice, especially where it is riddled with crevasses or overhangs. Using infrared imaging from aircraft, researchers have pinpointed several hotspots that have intensified over the same period as the uplift. These zones are in areas where fumarolic activity is known, but the current heating exceeds seasonal norms. The fact that thermal changes are occurring in tandem with ground deformation strengthens the case that magma is moving upward rather than that the mountain is simply settling from tectonic stresses. From a hazard mitigation perspective, one of the most urgent tasks is refining lahar modeling in light of the new deformation. Lahars do not need an eruption to form. They can be triggered by flank collapses or sudden ice melt from geothermal spikes. The uplift could increase the risk of such collapses by altering the slope stability on certain flanks. Updated computer simulations are now being run using the fresh deformation data to project the potential paths, speeds, and volumes of lahars under various scenarios. The modeling incorporates river gradients, sediment loads, and seasonal hydrology to predict which communities would be in the direct line of danger and how quickly flood-like waves of mud could reach them. What sets Rainier apart from many volcanoes worldwide is the dense human footprint in its vicinity. Tens of thousands of people live within valleys that geologists classify as high-hazard lahar zones. Infrastructure such as highways, rail lines, and pipelines cross these same valleys, often following river courses that could become lahar channels. With a red alert in place, agencies must contend with the possibility that certain transportation links could be severed rapidly if a major slope failure occurs. The economic ripple effects of such an event would extend far beyond the immediate hazard zone, potentially disrupting regional trade and supply chains. The geophysical swarm beneath Rainier is also revealing intriguing patterns. While many earthquakes are clustered beneath the summit, others are occurring in distinct alignments radiating outward along the mountain's flanks. These alignments correspond with known fault lines and fracture zones mapped in earlier geological surveys. Such patterns could signify that magma is exploiting pre-existing weaknesses to migrate laterally as well as vertically. Lateral movement can be particularly hazardous if it reaches the outer edges of the edifice, where rock is less confined and more prone to collapse under pressure. Even the hydrology of Rainier is being scrutinized for clues. Springs and streams emerging from the base of the volcano are monitored for changes in temperature, flow rate, and mineral content. In recent days, several monitoring sites have detected slight increases in water temperature and shifts in dissolved ion concentrations. These subtle changes suggest that heated groundwater is being forced through new pathways, likely a consequence of the same pressurization driving the uplift. If magma continues to rise, these changes could accelerate, potentially destabilizing slopes or triggering smaller steam-driven explosions in hydrothermal areas. The broader tectonic context cannot be ignored. The subduction of the Juan de Fuca plate is a constant driver of magmatic activity in the Cascades, but the rate and nature of this activity vary over time. In some periods, magma supply is steady but insufficient to breach the surface. In others, larger pulses intrude into the crust, sometimes in multiple volcanoes along the arc. The current uplift at Rainier raises questions about whether a broader magmatic episode is underway in the region. Observers are keeping a close watch on other nearby peaks such as Mount St. Helens, Mount Adams, and Glacier Peak for any signs of correlated activity. Technological advances have made it possible to analyze deformation in far greater detail than in the past. Three-dimensional models of Rainier's uplift are being created using a fusion of satellite interferometry, LiDAR scans, and high-altitude drone imagery. These models reveal not only how much the surface has risen, but also how the deformation is distributed. In the present case, the pattern is asymmetrical, with the most pronounced bulge occurring on the western flank. This asymmetry could indicate that magma is pooling unevenly, or that structural weaknesses are directing its path in specific ways. Another line of investigation involves the rock's acoustic emissions, tiny ultrasonic sounds generated by microfracturing within the edifice as pressure builds. Sensitive infrasound arrays, positioned many miles away, can detect these signals even through heavy atmospheric interference. Preliminary analyses suggest that microfracturing rates have spiked in synchrony with the uplift. painting a picture of rock layers under growing strain. These fractures could act as conduits for fluids and gases, further altering the internal dynamics of the volcano. The alert has also triggered a flurry of collaborative work between national and international volcano observatories. Rainier's current episode is being compared with deformation events at other large stratovolcanoes, such as Japan's Mount Fuji and Italy's Mount Etna. While each volcano has unique characteristics, patterns in uplift rate, seismicity, and gas emissions often share commonalities. By studying these parallels, scientists hope to refine their understanding of how far in advance such signals may precede an eruption, or whether they sometimes resolve without surface activity. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Mount Rainier's sudden uplift? Will it erupt soon? We want to hear from you. Thank you for watching, and see you next time.